Hi everyone, I'm Willian Freire. I'm from the State University of Maringá, and I'm here to present the work entitled Evaluating Machine Learning Algorithms in Representing the Decision Makers in Search-Based PLA Design. The software product line is an approach that provides artifact reuse based on a common infrastructure composed of core assets containing similarities and variabilities. The product line architecture, the PLA, contains variation points, variabilities, and variants, supporting the design decisions regarding the customization and adaptation of software systems for different contexts. So, a PLA needs to be generic and flexible to allow the configuration of the products that derive from the SPL, which makes the PLA design a people-intensive task. The search-based software engineering techniques are especially useful when dealing with complex software engineering problems. In this context, the multi-object optimization approach for the PLA design, named Mo4PLA, was proposed to optimize PLA design using search-based techniques and architecture metrics specific to the context. The Mo4PLA produces a set of solutions that have the best trade-off between the objects. Despite the applicability of the Mo4PLA has been demonstrated in previous studies, the obtained solutions in search-based software engineering are rejected by the decision maker, the DM, in some cases because many aspects of the problem cannot be mathematically modeled. In this sense, the incorporation of DM's preference into the optimization process is the recommended way to solve this issue. The Mo4PLA supports human interaction during the optimization process, in which the DM may evaluate optimized solutions according to its preference. Although evaluating all the solutions generated during the optimization process is unfeasible, the DM fatigues a limitation in his work, mainly because of the high number of interactions, the complexity of the evaluation of a PLA, and the excessive time required to complete optimization. Machine learning models have been used to prevent the human fatigue. These models are trained to learn DM's preference, taking the role of the DM after a number of interactions, evaluating the PLA solutions. The performance of these algorithms varies according to the problem, and the evaluation of different algorithms in this context is an explored gap. So, the main object of this work is the evaluation of different machine learning algorithms or a combination of these algorithms to build a machine learning model for interactive search-based PLA design. And a research question is, which algorithm or combination of these algorithms present the best representation of the DM profile in interactive PLA design optimization? This figure shows the design of our study, which consists of a quantitative analysis in which is collect accuracy and processing time measures to compare the results obtained by different implementations of the machine learning model. To accomplish the goal of our study, we proposed two questions based on GQM approach. The first one is, which is the best machine learning algorithm in terms of processing time? And the second question is, which is the best algorithm in terms of accuracy? The data instance is composed of architecture attributes from the PLA, and the class that identifies the evaluation of the DM. I won't go into details so as not to take up too much time for the presentation, but in summary, the class 1 represents elements from the PLA that cannot be modified by the search process, and the class 0 indicates elements that can be modified during the optimization process according to the DM's preference. We analyzed the distribution of class per DM, and we noticed that the distribution of the data is unbalanced. There are more class 0 than 1. We also analyzed the CPU time to train the machine learning models, and we observed that the K-star takes advantage over the other algorithms. That happens because this algorithm is a lazy learner. That is, the model training time is faster, but the classification time is longer than the other algorithms. When analyzed the CPU time to classify a new instance, it was possible to observe that the MLP and LMS took less time to classify. The observed values show the advantage of models based on linear combinations. These figures summarize the time to train and classify instances. We notice that the more number of instances to be classified, more growth of time for K-star, SVM, and ensemble models. The MLP and LMS models' time was linear, and the time difference is even greater as the volume of instances increases. So, answering the first question, the K-star model presents the best results of training time. The LMS model presents the best results for training and classification time. It is worth mentioning that in our work, the training time interferes with the DM fatigue. Now, analyzing the accuracy of the models, we notice that the K-star, home ensemble, and head ensemble models presented a similar CCR value, and the head ensemble is composed of K-star and home ensemble models. Also, the LMS present the worst CCR. This table presents the values of the F1 score for each ML model and DM. As can be observed, the K-star, home ensemble, and head ensemble models present the highest values and were more consistent than the other models. Again, when analyzed the accuracy measures for each model, these three models outperform the others. So, answering the second question, considering the accuracy measures, the home ensemble presented the best results in our interaction. However, the values are very close to the K-star and the head ensemble, and there is no statistically significant difference between them for most DMs. This was tested by using the parity test. When comparing to the baseline, the home ensemble, head ensemble, and K-star were statistically better. Regarding the training time, these three models also outperformed the baseline, and the K-star model outperformed the others. So, answering the research question, based on the empirical results, also considering the trade-off between accuracy and training time, the most adequate model to our proposal is the K-star. It outperformed the baselining, presenting a reduction of the training time, being similar to the best models. As a conclusion, the results demonstrate that the K-star provide the best model, considering the trade-off between accuracy and processing time. Furthermore, compared to the baseline, the K-star presented the best results. For future works, we need to conduct a qualitative study using real SPLs, with the participation of DM, evaluate the quality of PLA solutions. Thank you.